Okay, so it's time to talk about sound. You already probably saw that video, hopefully you watched it, you're supposed to, about the gentleman who was hitting the metal bars and stuff like that. I have one here. You could hear, if you can hear that or not. But I like sound. I like sound because there's so many different demonstrations you could do. We normally take an entire day of just doing demonstrations. It's cool to, like, things that you don't think would happen do happen. And I already did this, I believe, where you have two tuning forks that are exact same, and you hit one, and you stop, and the other one you could actually hear. You'd call that resonance. But I'm going to try to do a couple demonstrations and see if you could actually hear it on the iPad, which I doubt, but we'll try. All right, so sound. What is sound? If you think about this tuning fork goes like this. Okay, if we slow motion it, or in class we'd use a strobe light on it, you can see it go. So when it pushes out, it compresses the air together. When it pulls in, it stretches the air. We call those compressions and stretches, or compressions and rarefactions, not fractions, rarefactions. Okay, so there you go. It's a perception. Sound is a perception, okay, that the brain interprets, okay? It's kind of cool how the brain works, but we'll leave that to another time. The high molecular density and the low molecular density. High molecular density when it goes out and it pushes the air together, and low molecular density when it stretches it, when it comes in and it stretches the air around it. I'll show a picture of this coming up. This is kind of a neat thing, all right? So we play guitar string. You know, and that guitar string is actually a transverse wave, but it produces a longitudinal wave, I assume, think about it, because as it goes up, it's pushing that air together, and then it stretches the air, and then pushes it, and then stretches it. There's an example. So our tuning fork goes in, you can see that the lines are further apart, and when it pushes out, it's making them closer together. Okay, obviously you're starting here and you're working yourself that way. So out, compress, pull in, stretch. The strobe light's pretty cool if you ever get a chance to take a tuning fork and put a strobe light on it. A compression or a condensation. Now, when we talk about compression waves or longitudinal waves, a good way to show is with that slinky. And so if we had this across two tables, it's really big, really big. And one student was holding it, and then the other student was just pushing back and forth. It's hard to even see it here. It's like this. That's how we'd actually do it. You can see that no part of the actual slinky goes all the way to the end. The energy transfers, and the particles of the slinky, the metal, just moves this way. It transfers that energy. But this is a longitudinal wave going like this. We normally just draw it as a transverse wave. Why? It's easier. We always think of waves going like this as just easier. All right, so high spots, crests in the transverse are here. Troughs are places of rarefaction, okay? Rarefaction, they have this range here. I normally say it's like right here in the middle, okay, when it's stretched as much as possible. Yeah, I didn't know this. I looked this up a couple years ago. I thought it was fairly interesting. Longitudinal wave in liquids and gases, but can be both longitudinal and transverse in solids. All right, pitch. I got two tuning forks here. I have that's not it. I have a 256 and a 512. One has half the hertz as the other. This has half the hertz of this. And if you could hear that, it's definitely a higher pitched sound. I always feel a little funny when I talk to students here versus other schools I've worked at, where so many of you play instruments, and you could tell me something about what pitches and that sort of thing. But high frequency, high pitch, low frequency, low pitch. All right? Now, audible range. So I mentioned this, I believe, in another video, but here's how it went. When my second student teaching placement, there's a teacher there who's older, okay? He's retired now. But he had like a speaker to play different ranges of frequency, and he would start really low frequency and go to very high frequency. And so he would tell the students, okay, when you can hear this, raise your hand. And so one by one, as he starts to have the frequencies, let's say, go up from 0, up, 1 student, 2 students, 3 students. He's like the last one. I even raised my hand at one point. He was the last one, okay? So he could only hear a higher frequency. Other kids could hear real low, or the kids couldn't. Then you were supposed to put your hand down when you couldn't hear it anymore. So everybody kept their hands up. His was the first hand to go down, and mine was probably the second. But anyway, then kids after that started to go down, okay? I was pretty close to their age, though. I was, 23? They were 18, 22 or 23. But anyway, what this means is the older you get, the narrower your range of hearing is. I think that's pretty typically known. Now, infrasonic means below, ultrasonic means above. Now, somebody here can tell me dog whistles have to be ultrasonic, I believe. So if you've ever seen, I don't know if people have dog whistles anymore. I haven't seen any. But if you've ever seen Teen Wolf, the original, if there's a new one, I'm sure the original is better. But in the original Teen Wolf with Michael J. Fox, his dad owns a hardware store. He's at the store one day, and he's like, it's loud. And a student, he walks over to another aisle, and he sees a boy blowing on a whistle, and he goes behind him, and he hits the back of his head, and the whistle comes out. And the kid's like, "Mister, this whistle's broken." And he's like, and the kids walk away, and he looks, and it's a dog whistle. But the kid couldn't hear it, but he could hear it because he was a werewolf at the time. But anyway, there's a story for everyone to hear one. Well, there's a picture that looks like bio to me. Okay. So here's our measurements, our formulas for speed of sound. If you notice, they're the same exact because sound's a wave. And here's the equations for waves. Speed of sound depends on the material. I already mentioned this in other ones, okay? But here's an even, see this down here, general pattern is that solids, then liquids, then gases, as far as speed, okay? Solids the fastest, liquids next fastest, gases slowest. Right? So there's a little chart, you can take a look, you don't have to write them all down, but there's our general pattern. All right, temperature. So at 0 degrees Celsius, 32 Fahrenheit, 331 meters per second. So when we heat up the air, sound moves faster, okay? And so this is the equation right here. Sometimes you'll see it written differently, but this is how I write it. I know the line doesn't go all the way across, so I put that one down there, all right? So when we do these, if we do these, you can just use 331 and 273, all right? So here's the original at 0 degrees. Here's this correction thing here, though. So if we put in down here, we put in 0 degrees Celsius. 0 over this is 0, plus 1 is 1, square root of 1 is 1, times 331, there we go, okay? So if we're at 20 degrees Celsius, which is like a nice room temperature, 68, 69, whatever it is, Fahrenheit, obviously we get a number greater than here because this would come out to be greater than 1. Intensity. A lot of times when people are like, oh, it's loud, like this is intense, it's loud. To a certain extent, loudness is kind of a perception that we have, you know? I think something's hot and you don't, okay? Same thing with loudness. And loudness really is in reference to the amplitude, okay? Intensity, on the other hand, is a mathematical measurement, okay? So there's no debating, oh, do you think it's loud or not? If you're in a stadium and you're like, oh, it's not that loud here, and your friend's like, oh, yes it is, well then you find out it's 110 decibels. See, it's it's just a sensation that you feel. But when we actually get down to numbers, we call that the intensity. All right? Here it is, the equation. Intensity equals the power divided by the area. Power, and it's not written down here, I don't believe, but power is measured in watts. Area is measured in meters squared. It's watts per meter squared. It's okay, don't worry about it. Here's why. Does anybody know what the loudest stadium is, outside stadium in the NFL? I thought it was like Seattle, not Dome, outside. Maybe Kansas City? I think they get up, probably wrong here, 120 decibels. It's extremely loud, okay? So we tend to measure decibels for intensity, right? This is intensity right here is known as the threshold of hearing. It's like the faintest sound a human can hear, and this would be the intensity or the power per area, meter squared, watt per meter squared of whatever situation. And you'll notice it's a log function. So here's the thing. If we go from 0 to 10 decibels, it'd be 10 times greater. If we went from 0 to 20, it'd be 10 times 10, 100 times greater. All right. That is a little d and a capital B, decibels. Here's our chart. So if I'm comparing a floor fan to an air conditioning unit, 50 to 60, air conditioning unit, 10 times more intense. If I said louder in there, ignore that. 10 times more intense. If I go from 50, let's say up to 80, a vacuum cleaner, it'd be times 10, times 10, times 10. So it'd be times 10, 10 times greater, 100 times greater, 1,000 times greater. I'll show that here in a little bit. So maybe leave a little space there and I can show that. So yeah, here's the threshold of hearing, faintest, and the threshold of pain. I always used to say to students, I don't know if this is the point at which blood's coming out of your ear or what, but it's the loudest they could possibly tolerate. Okay. It's a wide range, you know. We're talking about 12 zeros, right? 11 zeros. That's quite a bit of range. All right, we'll come back. Let's try to do it here. I'm not going to do these for now. What I want to try to do is just show the decibels real quick, how I would do it. Oh, there it is. Can you tell this is actually like the second or third time I went through this video? I erased the other ones. So let's say we're at 50 decibels. And we're going up to 80 decibels. So we went from 50 to 60 to 70 to 80, right? So this is 10 times, 10 times, 10 times. So it'd be 10 to the third, right? 1,000 times greater. So 30 decibel change, 1,000 times greater. So look at this. This is a 30 decibel, right? So 80 minus 50, 30 decibel change. So what I normally tell students is this. If you're struggling, whatever, just remember, times 10. Subtract the 2. You'll get a number. Hack off the 0. And that's how many times greater it is. But for every 10 you go up, you have to multiply. You have to multiply by 10. And I don't know how to get back to the PowerPoint. Doppler effect is kind of a cool thing that happens too with sound. If you've ever been to a racetrack or you have an ambulance go by you or whatever, you hear this even an ambulance sound sort of makes that. It goes from this high pitch to this lower pitch, okay? And we can do calculations and whatnot, but see this point right here? Imagine you're going like this with your finger and you're making these point source waves. This must be going like this way, so moving like this. So what happens is the direction it's moving, these wave fronts get closer and closer together. It creates a high pitch, and then they're stretched out behind it, leaving a low pitch. I was trying to like think about, can we do it with this? Even if you're going like this, like me here, I could hear this little change, subtle change. Here we go. Okay. Movement of a source, meaning the one producing with a stationary observer, and the movement of an observer with a stationary source. So this is our source. The source is moving. That's the first one. If this was and I was moving somehow, that would be the second one. Okay? So even if somebody were like to be talking to you and you were to run past them sprinting, you would probably hear this change in pitch a little bit, not just the loudness, change in pitch. And here's the equations for that. So velocity of the sound plus velocity of the source. Okay. Plus is, I'm sure if it's moving towards you, minus if it's moving away from you. Same thing down here. Okay. And this OBS stands for observer. Sonic booms. Okay? When the velocity of the source gets close to the velocity of sound, you could go on YouTube and you can find videos of this. It's pretty slick to see. If you see a jet aircraft and you see this build up, basically, okay? It's a condensation that forms, or that you can see. And these are real pictures, okay? So what happens is it's giving off sound. It's giving off sound. Now, as the jet approaches the speed of sound, all of those wavefronts are getting closer and closer and closer till they're right on each other, and then you hear the crack or the sonic boom. People all say like a bullwhip, and whoopsh, whoopsh. Same idea. You hear this loud crack, and you can actually see this if you go on. I saw it was the Blue Angels maybe, or somebody was flying really low, like off the ocean or over a lake for like a crowd, and you can see this condensation forming. See, it says right here, they made visible by like condensation, like the air droplets in the air, disrupting. Bow waves. Okay, so bow waves. I wish I could draw this. Basically, as the plane, let's say, goes faster than the speed of sound, it creates these waves behind it, and they almost form like a V. So it'd be like a small wave, bigger, 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 because these ones are spreading out, right? So it creates this V shape. So you ever hear Mach? And in my engineering class, I'm going to have them watch this video on the SR-71 Blackbird, greatest, maybe you could call it the greatest biplane of all time. It flew so fast and so high that it could not be shot down, okay? But it basically went Mach whatever, 3. I used to know, I don't know anymore. But the velocity that you're traveling divided by the velocity of sound. So if you have Mach 2, you hear, oh, Mach 2, you're traveling twice the speed of sound. All right? So that's it for that. Let's try to run through some demonstrations. It's a terrible background to look at. So here we go. I already did the one, and you're never going to be able to hear this. 2 tuning forks. You hit the one, and then you could hear the other one. I don't know if we could see this. Got my big box here. When I hit it, pretty loud. Got another one. So I'm just gonna hold this one. That doesn't sound good. If I feel this box, I could actually feel it vibrating. Now this is only because I think these are both 256. Ready? If you could hear it. It's real faint. I could hear it. Okay? So that's called resonance. So they say if you have two pendulums and they're both hanging from the same rod, okay, and the one's swinging, it's the same length, the other one will start to swing. I've tried many times to get it to work. I can't get it to work, but it's true, it would. Okay? Another thing, we use resonance whenever you play an instrument. If you think about a person playing a trombone, I think my brother-in-law might have played a trombone. Anyway, or when you're playing keys on a woodwind, whatever it's called, or you're holding strings in a certain place, you're causing like basically resonance in the air. Okay, it's producing the same frequency over and over again, causing it to build up. This is an open-ended tube. Obviously, they're both open-ended, but let's see if I can do this. Let me come around here first and see if you can actually see this. There we go. Nice and messy. So, I'm going to hit my tuning fork. I can still hear these vibrating. If you could hear that. So when we get just the right column of air, okay, we form this resonance. See if we can hear it get louder. Well, definitely got quieter. Terrible. And then you'd measure the column of air, and you could actually figure out the speed of sound based off the frequency and the column of air. Okay? I'm going to do that in another video, and we're actually going to use it, not this, we're going to use a closed-end tube. We're going to use it for a lab. I'll take the data, you do it. All right?